Okay, let's talk about Chapter 10, Joins and Overlay. What are joins and overlay? Well, one primary use of GIS is to combine layers of information. Things like slope and rock uh, competence maps should be combined to study things like landslide hazards. It's only when you have certain combinations of geology and certain slope that hey, we've probably got a solid rock contact near the surface, and if this slope, when it becomes saturated, the landslides become more likely. Joins and overlays both combine data tables from two sources. There's just one big overarching difference, and it has to do with how features overlap. Okay, when you join features, they remain whole, and when you do an overlay function, if one feature crosses over another, they simply split those features to create two new features, and then those new features have the properties from both of the parent layers. Because basically what we're doing is ensuring a one-to-one cardinality, and this avoids the necessity to do things like summarized joins. So let's review a little bit about a table join, how it works. To join data from one table to another, you simply have to have a common field. Common field does not mean that it has the exact same name. It means that they have to have the exact same data. And so it doesn't matter whether you call it state FIPS or FIPS state. If the identification numbers in there are state FIPS numbers, so that a 13 in one means the same thing as a 13 in the other, then you can join them together. In which case you get a nice table, looks just like what you see here. Joins, it's always key to remember, are temporary. They get wrapped up in targets and joins and all this kind of stuff. Start with the table that you want to add information to, and then you join stuff to that table. That's the easiest way to explain it. So if you've got one data set and you want to add other data to it, you start with the one that you want to add stuff to, and then when you go through the process of creating the join, it will ask you what you want to join, and you'll select the other data set, and then select the fields that you're going to be joining by, and so forth. Spatial joins are a little different. Spatial joins records are matched using a spatial relationship instead of a key field. So instead of saying, well, we're going to match this to this because of this field in a spatial join, what we're doing is we're going to match this data to this data based on spatial location. And so that's what turns out to really matter. The issue, though, is some of the relationships are the same variations of spatial operators, so it's not always a straightforward kind of thing, and sometimes you have to deal with things like intersections and proximities and containments. In other words, does this intersect that? Is this within a distance of that? Is this inside that? Am I joining something else because it's the closest to it, or does it have to be inside of it, or does it just have to cross it? Spatial joins can get really complex because you have a lot of options. And so they give you a lot of freedom in terms of how you set them up and structure them and what you're trying to get out of them and what those options ultimately give you. But the one thing it doesn't do is split items and create this forced one-to-one cardinality. You can still end up with summarized data, and that may not be what you want. We'll look at a couple here. Intersect parcels is a target, so the new parcel feature class is created. The zoning records that intersect each parcel are then attached to that parcel. Okay, but if you have more than one zone in there, what's it going to do? Well, that's a problem. Proximity, cities is the target layer, new feature class of cities is created. Each city in the output contains all the information from the closest airport. A field is added, it records the distance and do some other stuff. That works good. Containment, septic systems are point features, and you simply want to know what geology unit they fall in. So how many pooping tanks are located on whatever kind of geological deposit. Yeah, it has to be inside of it in order for it to count. You'll get a number. There was 6 of them. There was 7 of them. There was 8 of them. There was 1. Whatever it is. Um, Comparison of operators here. In this example, the intersect and the within operators give nearly the same output. They would only differ if a septic landed on a boundary, in which case the within would excuse me, would yield a null field, and the intersect operator would have 2 matches. So that's where it becomes kind of important that you're very thoughtful about selecting some of these specific language operators within a spatial join. Now, cardinality in spatial joins is important because a lot of times we need one-to-one cardinality because we don't want to lose data. But sometimes it's the opposite. Sometimes we want to compile data. We want to combine data. And in which case we can do spatial joins where, for example, we might pick all the cities in a state because we want to ultimately calculate up, for example, what percentage of the population of Washington State lives in quote-unquote urban areas. And how would you define urban areas? Cities in Washington with a population over X number. And so you create that data set. You then join that data set to Washington. It's joining multiple things to one thing, in which case you don't have this one-to-one cardinality, so it can't do it directly. It has to summarize it, so it would then tell you how many cities and what they're, and you could tell it that you wanted to do sums, and so it would sum up the populations of all those cities. But you would also have from the original data set the population of the state itself, and so then you could add a field that would calculate the percent urban, and you could then do that. So there is no one tool that's perfect for everything. Everything we do in GIS is a combination of the tools that we have at hand to work with. It's a lot like painting. When you do the lab exercises and the tutorials, it's paint by numbers. We're saying, now take this tool and use it to do this thing to answer that question. See, wasn't that cool? And ultimately, at the end of the day, after you've painted enough pictures of dogs playing poker by numbers, you get to your class project, you get a blank canvas and a set of paints and a brush, and you get to decide, where and how goal number 4 starts and stops. How do we manage cardinality? Spatial joins come in 2 types. When it comes to handling these one-to-many cardinalities, you can create multiple copies of the target feature until there are enough for each matching record in the join table, or you can summarize it. Multiple copies is not typically that useful. Joined works, but there are some issues. Multiple copies is also called one-to-many. I guess I said earlier that doesn't, not the best option. Every type of join that we're going to look at here, that you're going to read about in the textbook, that you're going to examine doing the tutorials with Price, all of them are perfect in some situations. So it can get confusing with this notion of one-to-one and one-to-many and many-to-one and many-to-many. And so here's kind of how I sort of think about it in my head. And it doesn't exactly line up with what they use language-wise, so bear with me. You can take one feature and join it to multiple features and maintain a one-to-one cardinality. You can take multiple features and join it to a single feature, but if you do that, you have to summarize the multiple features. You can also copy a bunch of things to a bunch of things and keep a one-to-one, and that's not a problem. You could, for example, also merge a bunch of stuff down and join that with something else, and that would be easy enough to do, as long as you can maintain the one-to-one cardinality. You can also have sort of the flip of that first one you see down here. You can have a lot of features, and you can join information from one field to all of them. So the opposite direction of the way those arrows are running down there. You can literally take this one target feature's information, and for example, maybe it's the state of Washington, and inside you have all these cities. Well, not only do we want to know the city populations combined and summarized for the state, maybe we have some state information that we want to share with the individual cities. So we can take that one thing and join it to multiple things. All these are good options. All of them work. The tricky part's figuring out which one you need to do for the thing that you need to do. In the parcels and zones example, parcels usually lie within a single zone, so cardinality is 1-to-1. A parcel in two zones would be exception or an error in the way it was mapped or drawn out. A one-to-one join works well. There's no merge rules you got to worry about. When you run things and there is an issue, you'll a lot of times get a null field, meaning that there was something not quite right there. That doesn't mean it's necessarily wrong. It just means that it could be violating some assumption that you're making before you ran the tool. You can go back and look, and maybe it's something that can be corrected or needs to be corrected, or it might be something that you don't need to worry about because you're joining census data to state parcels in one data set, or the other also has a map unit area for DC or for the U.S. Virgin Islands or some other territory or U.S. possession, but it's not technically a state, and so one data set adheres to the definition of a state, one does not. You can end up with null values. Does that mean that everything's wrong? No, it just simply means there's no data that goes along with those other areas. And if those other areas are not something you're looking at, then it's not a big deal. Cities and airports is a good example of one-to-one, or it could be, because every airport can only be closest to one city. So it just looks at distances, and so for every airport, there's a city that's associated with it. Now, from a city, you can also identify its closest airport. Same kind of thing. Septics and geology, many to one is expected. A septic that lies on a geologic boundary would be a rare exception. One-to-one joins would work okay. There's no merge rules that's needed most of the time, but you could get that null thing if something is sort of, crossing boundaries there. Highways and soils, if you want to determine the soil characteristics of each highway to help maintain them, because some roads, for example, if you apply salt in the winter to fight ice and snow, it can cause the soils to become very compactable and shrink and swell quite a bit as moisture levels change, leading to cracking of the pavement and ultimately causing significant highway damage. So each highway, we would imagine, would cross a lot of these units, and so one-to-many is expected. If you do a one-to-many type join, it'll create multiple copies of each highway to match every soil unit, and that doesn't do squat for you. If you summarize all the fields and it'll tell you how many different types, that really doesn't help either. In a situation like this, what you really need is that ability to cut that road segment every time it crosses a different soil's boundary, so that each segment of the road has its correct properties, and that you can then work through all that. So here you can see the joint counts and how it adds it up and shows you different things. Again, workarounds, but overlay functions are superior. And so let's look at a classic overlay. Here we're looking at slope and rock, and we're trying to yield a feature class that has both. And so original slope polygon, you can see the top of the stack the competence polygons are in the middle, and then when you do the classic overlay, everywhere that a boundary from one crosses a boundary from the other, all the lines are maintained, and so that each polygon on the bottom layer has distinct and unique information from both. Nothing is lost, nothing is summarized, everything is one-to-one, and it's sort of the best of both worlds. Um, you can pick out individual polygons, and all the information from both things is there. It's pretty awesome. So let's look at some basic types of overlays. Basic types of overlays would be things like intersect and union. That's sort of the two biggies. Here we have inputs 1 and input 2. And so these are basically just two different shapes, and we're going to combine them and show you what that means. So if you do an intersect function between the box and the circle, the output is the common space to both, which is going to be the outside perimeter sort of shape of the circle with the cross lines from the box, because it's just going to keep all that stuff that is common to both and nothing else. Similarly, if we do a union and we combine these single two layers, and of course the thing we're trying to express here is that the center of both of these features is the same center, so they're going to lie directly on top of one another, in which case if we do the union, it's going to keep only the space that's common to one or the other. It keeps everything. If it's in one of the two data sets, it's in the output. Whereas with intersect, the only thing that's in the output is stuff that's common to both data sets. So let's look at what that kind of looks like. In union, the usual goal is to combine all the data to the extent the data set is the same. For example, you can combine, the combined table can be queried for combinations of values that are susceptible to geological hazard. And so what they've done here is they've looked at certain types of rock areas that they think are at risk for this, and you get the map that comes out of it because they've unioned the data, which means they've kept all the information from all the different things. Another example, this is, I believe, snail habitat, and so basically the way this works is you have elevation, you have limestone, and you have conifer data, and so you combine all this together, and the individual polygons maintain their integrity, but when the line of an overlay layer crosses across it, it then divides and subdivides further and further and further. Each one of these making less and less and less, smaller and smaller and smaller sized polygons. And each polygon has all the information. So once we combine the conifer, the limestone, and the elevation, every final polygon in the output, we know its elevation, we know if it is or is not in limestone, and we know if it is or is not dense conifer. And ultimately, based on how we combine those things or what we do with that, it yields us this snail habitat. Intersection and geometry, unions can only be performed on polygons on polygons. Intersection can be applied to all geometry types. A line and polygon intersection can assign geologic units to, for example, to a stream. Point and polygon can assign school district information to a house that's for sale or something like that. So there are other ways to use the intersection, but with union, they both have to be polygons. As far as the output geometries, just because you're limited to a certain type of things in your inputs doesn't mean that's what you have to get in your output. But it has to be the same or a lower order item. So you can't union roads and get line features and get polygons, or point features and get lines. But you can, or not union, I'm sorry, intersect. You can intersect, for example, polygons and get polygons, lines, or points. You can intersect line features and get line features or point features. And just like they say here with C, you can intersect lines and polygons, and when you do that, the lowest order item you have is the lines, and so your output can either be lines or points. You can't sort of upscale, upgrade, or uplevel the elements you're joining. So let's look at how extraction and overlay functions compare. What's the big difference? When we look at extraction functions, attributes are not joined. Extraction functions just give us this new output, but we don't really combine any information, whereas overlay functions do. So if we look at the intersect function, it takes the two data sets, it finds the space that's common to both data sets, it joins the attributes from both of those data sets and puts them in that common spaced output. Union takes all the information in data set 1 and all the information in data set 2 and combines them into output that has basically that exists in either one of the two or both and has all the attributes for each as they exist. When we look at extraction functions like clip and erase, clip uses the second input as a means of delineating what we're keeping. So it defines the area of selection and then it selects just that area from the original input. That's our output. Attributes, none of the attributes from the circle, just the attributes that came from the square. When we use erase, it's the opposite. It identifies an area in the original data set we want to eliminate. That area is eliminated. We're left with what remains. What remains has the attributes from the original data set, none from the other. If we go to the cookie in the cookie cutter analogy, the extraction functions clip and erase. When we use the clip function, we take the cookie cutter, we jam it down through the sheet of cookie dough, we get the cookie. The cookie only has cookie dough information. It has no cookie cutter information. We use the erase function, we take the cookie cutter, we slam it through the cookie dough, we throw away the cookie, we keep just the remaining cookie dough. The remaining cookie dough has the remaining cookie dough data, but none of the data from the cookie. Data quality is something that we consider. Data quality can significantly impact the results of spatial analysis. Boundaries that should coincide with county boundaries must. You have to maintain your logical consistency in all the things that can mean in terms of overpasses and underpasses and things that are coinciding, lining up and that kind of stuff, so that you don't have slivers or gaps or overlaps or dangles or undershots or any of those kind of things. And so how do we adjust that? We set our tolerances so that we can eliminate slivers and such things. XY tolerances is the way we do it. Vertices that are separated by a certain thing will collapse. This is almost a trial and error kind of thing. You set them too high with your tolerances and it will mess up things. You set it too low and it won't eliminate the things like slivers that you're trying to get rid of. So not always great answers, but that's what you got to do. Areas and lengths. Okay, time to climb up on my soapbox. When we do things, especially overlay functions, but pretty much anything else too that can change or distort a shape. Shape, area, perimeter, and lengths of features are changed. If we have a geodatabase, and these are fields in the feature class in the geodatabase, shape underscore length and shape underscore area are automatically updated. Okay? Two fields in a feature class in a geodatabase automatically updated. Everything else is not. Again, everything else is not. If it has any name other than shape underscore length and shape underscore area in a geodatabase in a feature class, it's not updated. If it has those titles, shape underscore length and shape underscore area, but it's in a shape file outside of a geodatabase, it's not automatically updated. Only those two fields in that specific instance are updated automatically. Assume all geometric measurements are incorrect. So how do we fix it? Manually calculate the geometry using the calculate geometry attributes tool and make sure everything is correct. How do we set up spatial joins? They've got this step through a series of questions What should the final output be? What's my target? What spatial operators? Um, I find this all taxing and confusing. Here's how I set up a spatial join. I have some data, and I'm looking at the data, and I'm thinking about what I'm trying to do, and I say to myself, at the end of the day, what information do I need to do what I'm trying to do, and where do I need that information to be? If you can answer those two questions, what information do I need, and where do I need it to be, you have everything that you need to start and successfully set up all your spatial joins. The information that you need is based about the questions you're trying to ask and the things that you're trying to solve. And so once you know what that is, then you can say, okay, where does that data exist? Oh, it exists with this, okay? But this is maybe a table, or this is maybe points, or maybe this is a line, or maybe this is a whatever. But I need this information to be attached to this other thing. This other thing might be a different size thing. A good example would be maybe we have demographics by census tracts, and I'm trying to figure out things by county. So what do I got to do? I've got to spatially join all the information from these census tracts to the counties that they fall inside of. Okay, and so once I know that that's what I got to do, the only other thing I have to do is be careful about how I do it. So if I'm going to do a spatial join, I have to think about those things like contains, completely contains, within, intersect, that kind of stuff, because what I want is for all the information to end up in the right place and not end up attached to the wrong polygon. And so you have to think it through. What do I need information-wise, and where do I need it? And then carefully select the steps within the spatial join that will do that. And then ultimately, once you figured out where you need it at, that's where you start. You go to that piece of data, and then that's where you go to start to establish your join, because that is the thing that's going to work from. This is just an example from the textbook. I'm not going to say anything much about this. You read the textbook and work through the tutorials, and this should make perfect sense. Here they're talking about how to set it up as far as the target and the joins and all this kind of stuff. Because the way that they're doing this using the tool as opposed to the way you used to in desktop of simply clicking on the data layer and doing the joins, starting the joins from there, figuring out what is a target is a little more tricky in what you're joining it with. So my best advice is, until you're comfortable understanding what they're meaning by target, you may have to do some of these things a couple of times and you'll get the output. And if the output is not ordered out the way you want, in other words, if you join the wrong information, all right, so we got two data sets. One has information you need, one has shapes you need. If you join the information to the shapes, then you have what you want. If you join the information from the shapes to the shapes from the information, you have the exact opposite of what you want. The moment you do one of these joins, it should be abundantly clear whether or not you joined it the direction and the way you wanted. And if you didn't, simply get rid of it, undo it, and then go the other direction. Here's some examples of results and what they can look like.